Ladies and gentlemen, it's my great pleasure and honor to welcome you to this afternoon session. My name is Herbert Mang, and I'm affiliated with Vienna University of Technology. We have 4 speakers this afternoon. I have the honor to introduce the first speaker. It is Professor Antoinette Maniatty. She got her entire academic education in the United States, starting with a BS at Rensselaer Polytechnic Institute, then 2 Masters of Science, one at the University of Minnesota and the other one from Cornell University, and finally the PhD from Cornell University. She has worked in a wide area of pertinent research, multi-scale simulations and experiments in materials, polycrystalline material simulation, to name just a few, inverse problems in solid mechanics, multi-scale modeling in manufacturing, and so on and so forth. She has received several honors. Let me just mention she's an elected fellow of the American Society of Mechanical Engineers. She has received several fellowships and so on. So you can read the title here, Computational Crystal Plasticity for the Design of Materials and Processes. I see many interesting names among the co-authors, among them Tony Ingraffias the first time, still from the times when I was at Cornell. So the floor is yours.
Thank you very much, Professor Mang, and to the organizers for having me here in beautiful Barcelona. It's wonderful to be in Europe and especially to be in Barcelona. So I'm going to talk about some of the work we've been doing for the last few years in crystal plasticity. I've been doing this for a really long time. This was my PhD thesis more than 20 years ago, so I've learned a few things along the way. I'm going to talk about some of the work we've been looking primarily in process design, but also thinking about design of materials. And there were some nice talks earlier by Professor Reza about, and Professor Wing-Kam Liu about the relationship between processing and properties and microstructure. And so that's very much in line with the types of work that we've been doing as well. I'm going to acknowledge my graduate students who did most of the work that I'm going to present, Devin Pyle and Payman Karvani, and just worked with a number of different collaborators over the years, Tony Ingraffia, Tony Rowlett, John Papazian at Northrop Grumman, Wojciech Michaluk, who does experimental work at Lehigh, David Littlewood at Sandia, and Robert Bondakoff and Leo Showalter, who are at Crystal IS. The work's been sponsored by DARPA, National Science Foundation, and the New York State High Performance Computing Consortium. So just brief outline, going to motivate the work here, although I don't think it needs much motivation for this audience. A little bit about the finite, the crystal scale model, finite element formulation. We'll talk about, give some examples in process modeling, some process modeling that's very similar to other work that you've seen here, the classical processing of large deformation of materials, polycrystalline materials, but also going to also give an example in the area of crystal growth where you have small deformations, but thermomechanical behavior and the plasticity and dislocation behavior is very important. And then, if I have time, talk some about performance modeling, fatigue crack initiation, and some few conclusions, and my thoughts on current challenges and future directions. So, as you know, how you make a material, how you make a product, you have to process it somehow to get it into the to get the material into the geometry you want, and that processing may involve large deformations, certain types of heat treatment, so thermal mechanical processing, and that leaves you with some type of microstructure. So you see the middle microstructure there on the left side is your typical rolled polycrystalline material where you've got very elongated grains from the rolling process. And that microstructure has a very large impact on the performance and service of that product. On the right-hand side, we have a crystal growth process. This is for making single crystal aluminum nitride. It's a sublimation process. The material is evaporated and then condenses on a seed crystal that's on a crystal holder plate. And again, the process parameters, really the temperature field and also the material that's used for the crucible and the crystal holder have a big impact on the properties of that crystal and how it's going to perform in service. In this case, aluminum nitride is used in ultraviolet LEDs. So, again, just summarizing, process modeling predicts microstructure features and defects, and that may be used to guide process design. And then the other thing that we're going to look at is understanding through modeling and simulation the relationship between the microstructure and the performance, and that can be used to guide materials design. So that's been a motivation for much of my work and probably many of you as well. So at the crystal scale, if we're thinking about a polycrystalline material, but it could also be a single crystal, you could look at any given crystal, and it has some lattice. And we assume that the deformation gradient obeys a multiplicative decomposition into the thermal, elastic, and plastic behavior or components. The plastic part, which is probably the most interesting part, we assume is associated with slip along crystallographic slip systems. So we have the plastic velocity gradient is a sum over all the slip systems of the rate of shearing on each slip system, gamma dot alpha, times the Schmidt tensor, p hat alpha. Hat indicates on the lattice configuration. That Schmidt tensor is the dyadic product of the slip direction and the slip plane normal. For small strains, if we're doing a small strain analysis, we do an additive decomposition of the small strain tensor, but our plastic strain rate has a similar form to the plastic velocity gradient, where now we're looking at the symmetric part. And the anti-symmetric part, of course, is associated with the lattice rotation due to plastic straining. So elastic behavior, fairly straightforward. We assume a linear relationship. The elastic strains in these materials is typically very small, so linear relationship is, for the problems we're looking at, quite reasonable. It's in the plastic deformation that the really interesting stuff happens. And that's why I can keep working on the same stuff for more than 20 years and still not really know what I'm doing. Because plasticity, as I tell everybody, is hard. So really, its dislocations are the heart of everything in plasticity, at least when you're looking at crystals. And so I start with the Orwan's equation. The rate of shearing on the slip system is the mobile dislocation density, rho m, times the Berger's vector for that dislocation type, times the dislocation velocity for that on that slip system, v alpha. That's an average dislocation velocity. And that dislocation velocity, v alpha, I assume that it's dislocation glide, power law relationship, with an Arrhenius term that gives us our temperature dependence here. Theta is the temperature, Q is an activation energy for dislocation glide. And tau alpha is our driving stress, the result of shear stress on the slip system. And tau hat alpha is, eta in this case, is the resistance to slip. I use eta here because eta is associated with the slip system type. So I'll talk a little bit about that more on the next slide. So the hard part of plasticity is how these dislocations form and interact with each other. Now, the mobile dislocations are assisting plastic glide. If you have to have a certain number of them for the glide to happen easily. If you don't have them, the material behaves somewhat brittly. The forest dislocations, the ones that are immobilized, are the ones that are hindering plastic deformation. So I'm going to give just examples. These are some typical types of constitutive models that we've been using for modeling the mobile and immobile dislocations, or the hardening, if you like, in our work. But there are many, many models out there with different levels of complexity. I would say this is maybe a medium to low level of complexity. We're doing some homogenization. We're not considering all the details of the dislocation types and every possible interaction, but we're kind of averaging it out using some sort of phenomenological ideas. So for dislocation entanglement hardening, this work is based on classic work of Kubin and Estrin, and more recently by Bayerlein and Tomei on hexagonal materials. So we have our resistance to slip tau hat has some friction component, which is, we assume, is fixed, plus some evolving component that's related to the force dislocation density rho f, that being associated with obstacle spacing. And so we have, and then we have evolution equations for our mobile and our force dislocations. The mobile dislocation equation, the first term is a constant source term. The second term is for, the second and third terms are minuses. The second term is when a mobile dislocation is immobilized by running into another mobile dislocation, so it's when a mobile traps a mobile. And the last term there is when a force dislocation traps a mobile. Now, once those dislocations are trapped, they become force dislocations, so those two minus terms in the mobile dislocation density evolution come into the force dislocation density as source terms. And then the force dislocation, we have a thermal recovery term that allows these dislocations also to go away with more quickly as the temperature goes up. Okay, so we group our dislocations by the type of slip system, so that's what the eta represents. For example, in a hexagonal material, we group the basal slip systems together, so eta 1 might be, when eta is 1, that might be the basal slip systems, and if we're looking at prismatic slip systems, eta could be 2, for example. Okay. We've also done some work looking at precipitation strengthened alloys. This involves the dislocations forming loops about particles, or precipitates to be specific, and of course those are there to give the material more strength. And what's interesting, I'm not going to go into the details of the equation here right now, but just kind of conceptually what's interesting in the difference between entanglement hardening and precipitation hardening is that in entanglement hardening, what happens is that the latent slip, the hardening on the slip systems that are not slipping is higher or equal to the hardening on the slip system that you're slipping on. So what happens is that the slipping tends to concentrate on the slip system that you start slipping on. So you get localized slip. When you have precipitation strengthening, it's actually the self-hardening is higher than the latent hardening. So what happens is once you start slipping on one slip system, the slip tends to move on to a different slip system, and so you get more different slip systems active and also a more diffuse plasticity. Okay, so we take these equations, we implement it in finite elements so that then we can solve on polycrystals or single crystals. Just some highlights of the implementation. We have both finite and small strain implementations. We use a 3D mix formulation. We have implemented it as a stabilized formulation where we interpolate both the displacements and the pressures with linear elements, linear tetrahedral elements, and we also have a one where we have quadratic tetrahedral interpolation on the displacement and linear on the pressure. The stabilized formulation gives us very good results at much lower computation costs, so that was the motivation for doing that. It's implicit with consistent tangent, parallel implementation. For doing our parallel solves, we use PETSI and NPitch from the Argonne National Lab. We have periodic boundary conditions. You'll see some of the examples show periodic boundaries. And we run our simulations on the BlueGenQ at RPI, Center for Computational Innovation, CCI. That computer is called AMOS, which stands for Advanced Multiprocessor Optimized System. AMOS also happened to be the first name of the first professor at RPI, who was one of the co-founders of our institute, Amos Eaton. And it also happens to, we're a fairly small school, but we actually have not as big as UT Austin, but in the Northeast, one of the largest supercomputing facilities at an academic institution. And we were the largest at one time. So we have very nice computational facilities at our institution. So I mentioned the stabilized formulation. Since Tom Hughes was here earlier, I figured I'd better say a little bit about that because based on his earlier work. So this is the finite deformation implementation. We have the divergence of our first Pula-Kirchhoff stress, 0. We split it into the deviatoric and hydrostatic parts. So we have our usual weak form where we enhance our trial function with this term here. It's very similar to the work of Hughes and others. When we then go through and derive our weak form, and integrate by parts, and whatever, we end up with a formulation that looks like this when you have linear elements for the pressure and the displacement field. Okay, so let's show some results. So in thermomechanical processing, what we're interested in is we're interested in getting the deformation microstructure because that affects the behavior, the strength, the anisotropy, fatigue resistance, as we'll see later when we look at performance, and the residual stresses at the microscale. What's really interesting is at the microscale, we usually see several hundred megapascal difference range in the stresses. And so you get huge local residual stresses that are going to then drive subsequent recrystallization and grain growth. We also see cell formation, which is interesting. We see, when I show the results, you'll see some of that. And it's these intragranular misorientations that drive, in addition to the residual stresses, that are going to drive recrystallization. The other thing that we look at is the effect of greater slip activity at higher temperatures. So microstructure evolution, here we're looking at aluminum alloy 7075, T651. This is a model with 107 grains as a periodic microstructure. And we submitted to plane strain compression to simulate rolling to a 20% reduction at room temperature. So we have the initial homogenized grain structure. And then on the right, we see the grain structure after deformation. Now the colors here are associated with the orientations. I have our legend there. And so what you see is initially each grain has a single color in it, but what happens after deformation, we can see that we start to get a range of colors. We see, like, for example, here we get this white region inside of this originally purple grain. And so what's happening is we're getting a cell forming of a different orientation from the surrounding material. Likewise, over here, we see this light blue region and this darker blue region. Here we're seeing this purple region forming inside of this. And so those are these, we're seeing the grains are breaking up, and those new grains, we would have misorientation as we go from one region to the next. And we can look at the misorientation, for example, on a slice through that polycrystal at some location. And we can see that we have some, and here we're not considering misorientations when we look across a grain boundary, only within the grain. So here we see a gradient of orientations occurring near a grain boundary, which is not surprising. We also see interior misorientations. Now, probably our simulation smears that out some. I think in practice, we don't have experiments that go along with this, but I think in practice you would see this to be more focused. not as diffuse. Okay. Here's another example. This one we did have experimental data, and this was an aluminum alloy 6063. And these are experimentally observed microstructures. So this is the homogenized microstructure beforehand. It has fairly random orientations. We see lots of different colors there. And the grains are fairly equiaxed. And then after a tensile deformation, we see that the grains are becoming elongated because of the deformation. And we start to see, some coloration variations within the grains due to misorientations, intragranular misorientations. And we also are seeing that certain colors are more predominant than other colors. And here's a simulation of a polycrystal. And so this was at 482 degrees C. So what's interesting is at this temperature, you not only have the 12 octahedral slip systems active, but it's been observed that you see slip also on the cube slip systems and on these 45-degree slip systems. Piershaw and Driver did some very nice experimental work. So if we model it with just the 12 slip systems, which would correspond with like a room temperature deformation, we see a behavior like this. We're seeing more breaking up of the grains. You can also see greater heterogeneity in the deformation. When we have this 24 slip systems active, we see, again, evolution of the texture, but less misorientations within the grains, and also we see a more homogeneous deformation. And if we look, what we were really interested in is that in subsequent recrystallization, the 001 orientation is the dominant one that appears. And when you only consider 12 slip systems, you just don't see 001 orientations appearing after the deformation, and that's what we see here. But in the experiments, it's clear that there is a 001 component, and that's a favorable orientation for nucleation of nuke grains and growth. And we do get that orientation appearing when we include all 24 slip systems. So we see something that's more close to the experimental observation when we include those additional slip systems. So just summarizing that section. So crystal plasticity, finite element modeling predicts to a certain degree cell formation, but the present model is not adequate for predicting dislocation patterning details. There's been other work, I think very nice work, by David Field and Mohammed Zabib at Washington State and Arsenlis et al., who have, they look at the individual dislocation types and are able to predict dislocation patterning by the details of those interactions, which we've kind of homogenized out in the formulation that I presented. The other thing we found was that at elevated temperatures, these additional slip systems leads to more uniform deformation and lower misorientations, and also the formation of this stable cube orientation that's favorable for recrystallization and grain growth. So adding those slip systems is important to predict that the correct texture, and then if we wanted to link this up to some type of grain growth simulation. The next in process modeling that I want to talk about, next example is aluminum nitride production. So aluminum nitride, single crystal aluminum nitride, is well suited for high power and high frequency electronic and photonic devices. It's a very interesting material, has very high bandwidth, and when used in a LED, it creates an ultraviolet light, which actually the frequency of that light is optimal for water and air disinfection, which could be used for water purification because of the low power requirements. It could be used in a variety of different types of situations, certainly in third world places, and also for municipal water supplies, which currently are using mercury-based sources. So certainly this would be a cleaner, more efficient solution. However, the cost of manufacturing aluminum nitride is really high still. And that's mainly because they get, there's two main competing methods to make it, an epitaxial growth, but the epitaxial growth has a high dislocation density versus the bulk growth. My colleagues at Crystal IS have developed this sublimation process where they get a much lower dislocation density on the order of 10 to the third per centimeter squared. So it's very low dislocation density, which gives a very long service life and also excellent performance. Problem is, when you have this very low dislocation density, the material is pretty brittle, and they have a real problem in their process with the material cracking, and they have very high residual stresses. It's done at a very high temperature, and so they're interested in understanding this process, to model the process, to understand what are the key factors causing that cracking, and at the same time, they don't want to introduce dislocation, so we wanted to develop models to guide the process design. So here's a sort of schematic of our model. We have the crystal that's growing. This is the crystal holder above, typically tungsten. The crystal is grown along the C-axis. It's hexagonal. The aluminum and the nitrogen each form HCP lattices that are intertwined with each other. The surface is treated as free, and we're interested, so the main metrics that we're interested in are the tensile stress on the M planes, those are the cleavage planes, and the dislocation density. So we want to keep both of those quantities low. And we wanted to see what the effect of temperature gradients and the crystal holder thickness are, relative importance. So the thermal expansion mismatch between the aluminum nitride and the crystal holder actually here is showing that as a function of temperature along the different directions, along the A and the C direction of the crystal. So this is the difference between the thermal expansion coefficient as a function of temperature. Let's see, the green is along the A direction. The A direction is the transverse direction. The C direction is the axis that they're growing. And overlaid is the stress on the tensile stress on the M plane. So we can see that it starts to grow a lot when we get a higher thermal expansion mismatch. Even though it seems fairly low, it has a very big impact. And actually, the people I was working with at Crystal IS, they did not think that that was going to be important, but it turned out to be the most important thing. But the temperature gradients also have an impact. We can see that we get this very high stress on the tensile stress on the M planes on the top of the crystal near the edges due to that thermal expansion mismatch. But when we have temperature gradients, we also see high stresses on the bottom of the crystal as well. And that correlates with the cleavage that they see. We also looked at the dislocation density, and what we found was that the radial temperature gradient leads to dislocations on the prismatic planes at the outer radius and at the bottom. And the thermal expansion mismatch, as one might expect, leads to dislocation concentration at the top crystal surface on the basal planes. The crystal holder thickness, we found, had a big impact, and that by thinning it down, you could greatly reduce the stresses that lead to cracking. And in fact, they did experiments then at Crystal IS where they varied the crystal holder thickness, and we see that as it goes down, it's from 4 times to 2 times to 1/4 the original size, one time, we see that the stress on the M planes correlates very strongly with the percent of failure that they were seeing. Okay. All right, we have to hurry up. Process modeling. So I just kind of went through all of that. So let me just quickly talk about performance modeling. This is looking at fatigue crack initiation. This is aluminum alloy 7075 T651. And there was an experiment, double-edged notch experiment, where they looked at particles that second phase particles that tend to crack and lead to crack nucleation in the material, and they tracked a bunch of them, and some of them nucleated cracks and some did not. So we simulated these. So this is one where the crack did not nucleate into the surrounding material. This is one that did. And we developed a damage metric that we looked at that seemed to be very predictive of determining whether or not the crack nucleated into the surrounding material. And the important thing is that we found this sort of a relationship. Now, the experiment looked only every few cycles. They stopped the experiment and looked where the cracks were. So we know, like, for example, here, this one nucleated between 30 and 100 cycles, here between 10 and 30. So the main thing that we found was that the number of cycles to nucleate depends on both the plastic slip damage metric and the maximum tangential stress on some non-local arc. In this way. So just some quick conclusions. This analysis can be used to predict macroscale behavior, local range of stress and slip, evolution of grain orientations and formation of intergranular misorientations in large deformation processes, so we can predict microstructural features and defects. With experiments, we can learn about the effect of different subgrain scale mechanisms on microstructure evolution, predict likelihood of cracking and dislocation density in aluminum nitride. Can be used for improving process design. We also used it to understand the relationship between microstructure and performance. Just some things that I'm really interested in. So there's really a need for more experiments at the subgrain scale. These are just starting to come on board. Early evidence shows discrepancy. So even though we maybe get some of the statistics right, locally we're not exactly matching up the behavior. And so better understanding of dislocation behavior, modeling that more accurately. So there's some good work that's coming on board on the experimental side that can help us to improve our simulations. Grain boundary mechanisms, doesn't have that in my model, but that's very important. And definitely there's a need for more stochastic analysis and develop of stochastic models. So I'll happy to answer questions. Put a quote from the president of my institute, the Rensselaer Polytechnic Institute's a diverse community of dreamers and doers. There's a picture of our place. Oh, it's beautiful. And it's in beautiful upstate New York, and I invite all of you, but not at the same time, to come and visit.